Yes, and we are back for hour number 2 here on Friday, the fourth part of chapter 22, finishing it off too. Keep in mind all these reminders here. We're going to do nitriles now, a little bit more on amides and penicillin, and show you nylon here in a minute. And then we'll get into the sample test 2. So here's nitriles, triple bond to carbon with nitrogen. And, why are these in the carboxylic acid derivative chapter? Well, you don't see the acyl group. There's no carbonyl, but there's 3 bonds to a heteroatom, to nitrogen there. And the reactions are similar to the derivatives we've seen here. So you can take water with either acid or base and go back to the carboxylic acid. You can do that for all of the derivatives, right? Depending on what it is. In the basic conditions, you go to the carboxylate. You can use LAH, lithium aluminum hydride, with a nitrile. And after quenching with water, you get the amine. Okay, now that's just like with amides, right? If you use LAH with amides, I think that's chapter 20, if I remember right. Remember, that's a reaction we covered before there with amides. But here, if you use LAH with a nitrile, you can go to that same product. Okay, so it's similar to that derivative there. If you use Dieball, one equivalent, what is Dieball? Ooh, that's another one of those acronym reagents. Diisobutyl aluminum hydride, sometimes Dieball H, whatever. After quenching with water, you get the aldehyde. Remember, there's only one hydride on Dieball. So mechanistically, you can already be thinking about this, how this is going to work. The Grignard reagents, if you have an alkyl magnesium halide and then quench with water, look, you get a ketone. Okay, so that's interesting how that goes, and that's after all these are after quenching with water. So let's see, which ones should we do here mechanistically? They're actually all the same. They all parallel what we've seen before. The one that takes the most time is the acid-mediated hydrolysis. We can do that. So let's see how that's going to work. So if you take a nitrile and treat it with water and acid, how do you get to the carboxylic acid? And what does the nitrogen end up as? Well, it ends up as, in this case, ammonium cation. Okay, so mechanistically, can you figure this out? Well, there's a lone pair here, so let's go ahead and protonate it. So it'll look like this. The protonated nitrile, and then what? Water can attack here and kick the electrons over. So what do we get? Hydronium ion there, and the lone pair on nitrogen. So we're already starting to look like a carboxylic acid there. Let's transfer the proton over here. And what do we get? We get the 2 protons on the nitrogen and a free OH there. And then what? Well, we've got water. So water can add again here. And what do we get? OH, OH, NH. And one of them has the 2 on. That's from the water that just went on there, right? And then we can transfer a pair of electrons on the amine to get another ammonium cation, right? And then what? Let's see, we can use lone pair on one of these to come down and remove the ammonium. And how does that come off? We break the pair of electrons, we got the plus charge on there. You see that will be NH3, and it's neutral, right? And so what occurs here? Well, we can grab the proton off here, and by doing that, we get the products, I think. Let's see, yeah. There's our carboxylic acid, and the nitrogen is in what state? It's ammonium cation. Okay. Yeah, I think that's a good exercise to be able to go through that, but it's very similar, right? You notice a couple things here, tetrahedral intermediate, right? Keep adding water. We're under aqueous conditions, and we are acidic, so you end up as a neutral carboxylic acid, okay? pK is 5. So if we're on the acidic side of that pK, it is protonated, neutral. And we're way on the acidic side of this. pK there is 9. So if we're down here around pH 1 or 2, that's certainly protonated. Okay, which other one should we do? How about the, let's see, how about the Dieball one? Let's do the Dieball here. And if we do Dieball, we have the 1 equivalent of hydride. And what's Dieball look like again? We need to look at that, right? Diisobutyl aluminum hydride, okay, like that. And it's neutral, right? It's just aluminum with a hydride on it. So how do we even get this started? Well, we can coordinate the lone pair there and get the nitrile aluminate complex. And I'm just going to abbreviate the two butyl groups there as R groups. Is that okay? But we've got some charges here we need to worry about. There's a plus charge on the nitrogen. And what about the aluminum? Yeah, it's an aluminate, right? Because it only has 3 valence electrons. So if you have 4 bonds to it, it's like boron, the borate complex we saw before. So what can occur at this point? Well, we can transfer the hydride over here. And by doing that, we get a carbon hydrogen bond. We get the neutral amine now and the neutral aluminum. Okay, so we go from the Lewis acid complex here, which is really we could call this what, an ylide, real? It's a zwitterion where the negative and plus charge are right next to each other. Now, it's not like the Wittig ylide, okay? But it's a type of zwitterion, you could say. And what is this? Well, we have the aluminum. That's how it sits until we quench with water, okay? So it just sits like this until we quench, and it only has the 1 hydride, so that's all it can do. Now, LaH, lithium aluminum hydride, has more hydrides here, and this could add to this imine type carbon nitrogen double bond and get what? The primary amine. Okay, so same mechanism holds for LaH and Dieball, except now we just have the 1 equivalent of hydride. Let's see what happens when we have water here. Water, we'll do a couple things. Well, let's be thorough about it. So let's go ahead and put the water on the aluminum, which is Lewis acidic, right? So we'll have the Al aluminum with 2 R groups and water on it now. And nitrogen, look like that. Oh, we need a negative charge on aluminum. Now, what can occur? Well, this is a metal nitrogen bond. So let's go ahead and protonate that nitrogen right there, okay? And by pulling this pair of electrons out of this nitrogen aluminum bond, we go back to neutral aluminum. And what do we go to here? We go to this, okay? And, you know, you can draw the rest of the aluminum. It's an aluminum hydroxide at that point. I'm not going to worry about that. That's inorganic stuff. That's boring. We're more interested in the organic stuff here. The inorganic aluminum hydroxide is done at that point. But we get this intermediate. Now, that's not the product. What do we say the product is? Right, the aldehyde. So how do we go from here to an aldehyde? Well, what is this, first of all? Right, it's the imine. Okay. So there's our imine. And we're under what? We're putting in water here. So, and if we acidify this a little bit, it'll go even quicker here. Then we could directly just protonate this nitrogen aluminum bond with the acidic. But if we put the water on there, right, it's acidic enough. In fact, the imine on its own with water is going to do what? It's going to hydrolyze. So imines with excess water and available what? Acid or base. If we're under acidic conditions here, we'll get the neutral aldehyde. There's our product, right? And what does the nitrogen come off as? Right, ammonium cation. Now, I'm not going to draw the rest of that. That's from chapter 21 when we talked about imines and enamines. And so an imine here, presence of excess water, little acid or base. Even if it's neutral, this will hydrolyze and eventually give us this. And how does that work again? Well, water can attack here, right? Transfer protons, get the nitrogen come off. You got to transfer a bunch of protons to nitrogen. to eventually get the ammonium part of that. But yeah, so the aldehyde product from that. And yeah, we won't do the other one. Let's do maybe the Grignard one. That one might be a little bit different. Let's do the Grignard edition here with the nitrile. So let's take ethyl magnesium bromide, okay? And then quench with water. And what are we going to get here? We're going to get ketone. And that's kind of unfortunate. They're both they look the same there, don't they? And then we quench with water, ammonium. Yeah, we are same byproduct. So what's going to go on here? Well, let's attack, okay? And what do we get? We get the ethyl group on there, and we get the nitrogen and the magnesium bromide. Okay. That's completely analogous to the Dieball mechanism we just did, right? Here we have this metal nitrogen bond here, and now we're going to quench with water, right? So let's go ahead and transfer the proton there. What do we get? We get the same thing again, right? We get the imine. And here's where the nucleophile went on, this part here to the nitrile. So again, I'm not going to draw the rest of those steps, but that will give us the product, the ketone there. And, you know, if we acidify, again, excess water, we're hydrolyzing the imine to the ketone product there. I think that's all we need to say about those. We already did the acid-mediated one. The base one's very similar there. And I think we can do that. Okay, back to amides a little bit. And amides, we already talked about how to form amides. Oh, maybe we didn't do this one. So how can we take an amide? Or no, carboxylic acid, sorry. And ammonia. Well, let's do ethylamine, okay? And let's heat this up, okay? And what can we get? We can get the amide. So again, the heat, 100 degrees, we're saying, yeah. And remember, if you said room temperature, this will just be acid-base chemistry. But if we're heating this up, we're getting a byproduct, water, right? So can we draw an electron pushing mechanism here? Okay, so the acid-base chemistry is going on here. So most of the time it's sitting like this. But, you know, part of the time we do have some free amine. And it has to be free amine in order for the nucleophilic addition to start here. So if we can do that, what do we get? O minus, N ethyl H2. Now that's not going to last long, right? Here you have a good base here that can transfer a proton quickly, but it's the same thing, tetrahedral intermediate, right? And we got N ethyl with just one hydrogen on it now. Now, what can occur? Well, we've got pairs of electrons here. Let's bring in the pairs of electrons and kick out hydroxide, okay? So we've got excess amine. We don't have any water in the reaction to begin with, right? We're generating a small amount of water as a byproduct. So let's see where that might come from. So let's see, we get the product here actually directly from that tetrahedral intermediate, right? And then we have hydroxide. So how are we going to get water? Well, we've got starting carboxylic acid. That would be the best source there. We've got this intermediate too, okay? So let's just say here's some acetic acid, starting material, and there we go. There's the part that will give us the water. So there's the two products, okay? And yeah, and then we form more acetate, right? That'd be the byproduct of that last step to form the neutral water. Anyway, this, you know, requires higher temperature. You begin to distill this off, and that's Le Chatelier's principle. As this is removed or distilled here, you'll favor the equilibrium toward amide formation. And the amide is the most stable thing due to resonance, so that's a good thing there. There's another thing that we can form here, and that's if we started with an ester, okay? So esters are less stable than amides. So like we said, within the hierarchy of the different carboxylic acid derivatives, you can always form a product that's to the right of whatever starting material you've got. So esters are kind of in the middle, and can we form an amide here? Well, a lot of times we do have to heat them up, okay? And it's the same idea here. I'm not going to go through the mechanism, but from ethylamine, we'd form the ethyl amide, and what would be our byproduct here? Where would the OME, the methoxy group on the ester, end up as? Right, it'll end up as an alcohol. And again, that's volatile enough you can distill that and get this reaction to go quite readily. So there are different ways to form that. Let's show a couple examples of this. More complex ester. Here's a cyclohexane methyl carboxylate ester. And let's react that. Oh, how about with this? How about a cyclopentylamine? And if we heat that up, what are we going to get, right? We're going to get methanol coming off, and we're going to get the cyclopentyl amide there for that product, and methanol again in that case. So somewhat versatile reaction, but again, you have to heat them up. The easier, the faster way to do this would be to react with the acid chloride in the amine, right? That would be probably the better way to go. All right, one other way to form amides here is to take the corresponding acid with an amine and DCC. Now, what's DCC stand for again? We have PCC, pyridinium chlorochromate, and now we have DCC, which stands for what? Dicyclohexyl carbodiimide, a different reagent. We used this when we formed esters with carboxylic acids and alcohols. Well, you can also use this strategy for amides, okay? So DCC here, if we have this carboxylic acid can add to the DCC, transfer a proton, and we've seen this before. I'm not going to go through all the mechanistic details here, but the carbodiimide intermediate would look like this, where these R groups are the cyclohexyl groups, and we call this the urea or the uronium. If you have this protonated here, it would be a positive charge on that. It's becoming urea. The amine then is the nucleophile that adds at this point, tetrahedral intermediate, have the thing come back down. That will give you the product here, and what is the byproduct? And this is kind of the key for why this reaction works. You form the dicyclohexyl, here I'll draw it out for you, urea, okay? This urea here, there's the elements of water right here, right? H2O, and that's what you would need to eliminate, right? You need to eliminate 2 hydrogens and this oxygen because it ends up on the uranium. The nucleophile comes in there, tetrahedral intermediate collapses back down, and then this grabs another proton right there. So that gives that second one there, and you can go through the details of the mechanism if you'd like. Can form amides or esters from carboxylic acids, and that. All right, let's look at. Oh, okay, let's do nylon now. We've got a demonstration. We need to see what we're talking about here. You've heard the term nylon. You've probably heard of nylon stockings. Well, nylon, yeah, that actually was one of the first applications of it. Women's stockings. Nylon is a very versatile material. It's a polyamide synthetic material inspired by peptides or proteins. In fact, in the 1930s, the structure of proteins were starting to be elucidated, and they were known to be formed from polyamides. So Wallace Carruthers at DuPont company there in the 1930s decided to make synthetic polyamides. He said, well, I know how to make amides. Let's see if we can make a synthetic protein that might have the same characteristics of that. So here's what he did. He took this material, which is a dicarbonyl carboxylic acid chloride, right? And that's from adipic acid. 1, 2, 3, 4, 5, 6. Yeah, 6 carbon diacid. But yeah, he took adipic acid and treated it with thionyl chloride. Okay, and that's a naturally occurring thing, right? So you can take adipic acid, treat with thionyl chloride, make the dye carboxylic acid chloride, and then you react that with hexamethylene diamine. 1, 2, 3, 4, 5, 6 diamine. Okay, and there are ways to make that from the dihalide and react with ammonia, or react with azide and then reduce the azide to the amines here. And when he does this reaction here, what occurs? Well, we get the acid chloride formations, right? So you can go through the mechanism there, and it's on both sides. So this can just continue. Once it reacts there, this amine on this end can react with another adipoyl chloride and put on another unit. So here's what the polymer looks like. And this was a real breakthrough because it's easily made, and it has the same properties as naturally occurring protein. And the protein that Carruthers was actually inspired by was silk, spider silk. They had figured out the structure of that, which was polyglycine polyalanine. And he said, well, I know how to make amides. So here's the amide, here's the adipoyl thing, and then there's another amine coming off here. So that's the repeating unit, right? X can be hundreds of units long. And then here's the hexamethylene diamine. There's another amide here, for example. And this is a solid material. You'll see these two are liquids. And once we have the solid, you can convert it to a number of things and make a lot of useful materials. So let's see if we can do this. We've got a nylon machine here, a little petri dish. And the first solution I'm going to put in here is the aqueous diamine. Hopefully I'm not going to spill it on myself. Fill up the petri dish halfway. And then we'll get the other part, top solution. I like how they label these things for professors. We got to keep this straight. Bottom solution, top solution. Top solution has the adipoyl chloride in it. And let's see, when we put that together there, it's actually in an organic solvent. The amines in an aqueous solution, so it's at the bottom there. But what you can see here and what begins to form at the interface between the two solutions is the white polyamide or nylon material, okay? And the rest is engineering from here on out. We got the chemistry going, and now we have this real high-tech nylon machine up here. We can pull that material, and if you see the interface here, it's forming it right where the two solutions come into contact. It's a very fast reaction, right? This is the most reactive derivative, carboxylic acid. And this is a very good nucleophile. So this reaction's instantaneous. You don't need to wait around. And you see this white material building up here? Okay, that's your nylon material. It's a little wet and has some solvent in it, but you see this white material here? You can take that and melt it down and mold it into whatever device you want or object you want, or you can extrude it and draw out fibers and then weave those fibers together to make nylon cords and whatever. And it wasn't just women's stockings. In World War II, they made parachute ropes out of nylon and a lot of other products, okay, that allowed for this to be made. By weight, it's as strong as steel. So it's very light material, and especially if you weave it together, it can be very strong material. And it's resistant to hydrolysis, so it will last a long time and can be recycled and reused. Anyway, there's nylon for you. Wallace Carruthers in the 1930s, a long time ago anyway, thinking about how to make amide bonds. All right, let's go back up here to the overhead and do a little bit on another amide that has important implications, actually a tie-in to World War II again. I'm not a big World War II buff, but these topics tend to come up quite a bit. Here's the structure of penicillin right here, penicillin G. There's all sorts of derivatives here. You can have different R groups here, but it's this cyclic lactam right here, this four-membered cyclic amine. Remember, a cyclic amide is called a lactam. It was originally discovered by Alexander Fleming in Great Britain. There's a great story about that, how he had the petri dish out on the windowsill. He's trying to culture some strep bacteria, and some mold blew in the window. And the mold, actually the penicillin mold, was the thing producing the antibiotic. And the mold was producing the antibiotic to try to kill the bacteria in his petri dish. So he had the insight to think, well, what is it in the mold that's actually killing the bacteria? And he isolated that material and found that it was a very good antibiotic. It killed a lot of different bacteria. And then he thought, well, this could be like the sulfa drugs. We could use this clinically to kill things. They didn't know what the structure was at all, but they could culture this mold and get high amounts of this. Originally, they thought this was the structure right here, which is two five-membered rings put together. It's not. It's this four-membered lactam, which at first people thought, no way, a little four-membered amide like this would be highly strained. That can't be it, but it turns out that's it. And that's the work of Dorothy Crowfoot Hodgkins right here, won the Nobel Prize for figuring out the structure by X-ray analysis. This was before the advent of computers, so her grad students had to solve all these equations by hand. So yeah, a lot of people got their PhDs solving the Bragg equation by hand to look at the diffractions of X-rays to get the 3D structure. And you see the little four-membered ring? It's right there. Okay. That's the lactam. And then at MIT, John Sheehan actually did the total synthesis of penicillin. They don't make it that way commercially. They culture penicillinic acid and then acylate this amine right here to make thousands of different types of penicillins. There's a whole bunch of these beta-lactams in the clinic. The most common one is penicillin 5. That's probably the one you've taken before. Thinomycin is a carbapenem. Instead of the sulfur in the five-member ring, it's a carbon right there. Thinomycin is more potent against different strains of bacteria. Cyclosporin, cephalosporin, sorry, not cyclosporin, that's a different drug. Cephalosporin C has a six-member ring here instead of the five-member ring. So a little bit different. And then this one lacks the amino side chain here, clavulanic acid. Nocarideciden A has a different structure here, has an oxime, which is kind of unique. But all of these materials, all of the beta-lactams, their mode of action all involves the four-membered ring. And like I said, this is a unique ring. Most amides resonate here in the IR down at 1670 due to the resonance. But these beta-lactams, or these four-membered rings, resonate way up at 1750. And that's because this resonance structure is not favored now. Why? Well, that would be sp2 hybridized, and it's harder. It'd make it even more strained here to try to constrain this to what, 120-degree bond angle? It's already at 90, right? So having this lone pair resonate over here is not favored now, which keeps the bond order very high for the carbonyl. In fact, it's 1750. And this is actually accentuated if you have another ring on here. This lone pair is sp3 hybridized. It cannot resonate over there due to the ring strain. Anyway, here's how penicillin works. It's acyl transfer, carboxylic acid derivatives. So that's why we're talking about it. And you need to know the basics of it here. My graphics are again on Learning Suite. You can see the whole story there. But let's look up here and see what goes on in a typical bacteria to make its cell wall. Now, these are single-celled animals, so they have to have robust bacterial cell walls. And they have different building materials to make their cells. They make this cross-linked type thing here with a D-alla-D-alla glycopeptide cross-link. And the D-alla-D-alla is referring to the two alanine amides right here. Those stereocenters are different than higher animals, okay? Most alanines are not D, they're L in higher animals. But in bacteria, it's actually the D-alla, okay, which is right there. And we'll say more about that when we get to get to peptides and amino acids, whatever. But the enzyme here is called a transpeptidase, which actually has to interact here and break open this amide bond right here. And this is an enzyme, so it can do that at room temperature, and it forms initially a ester with the enzyme. So it's a covalent linkage to the enzyme. This big ball here is hundreds of amino acids. And the byproduct here is one D-ALA unit. And then there's another glycopeptide here, which has an alanine unit on it. I'm sorry, glycine. And then that does the attack here and then forms the cross-link. The two glycopeptides are very complicated things, which create the robust cell wall in the bacterium. So this is the normal pathway which is going on in bacteria to keep them alive. Now, what does penicillin do to this? Well, it's a molecular monkey wrench. You throw that into the works and it gums things up and shuts down the cell wall synthesis. How does it do that? Well, it interacts with the enzyme. The transpeptidase enzyme has a primary amine. It's a serine amino acid that will add to the lactam and form the ester right there, an adduct of the actual drug, penicillin. Remember, penicillin comes from mold, not from the bacteria. Okay. Mold and bacteria are in chemical warfare with each other. They're trying to kill each other off. Well, create a niche in the environment that they can thrive in. So mold produces this. This is toxic to bacteria. And then we co-opted it and used it as a drug, right? Why? Because it shuts down the cell wall synthesis. It takes the enzyme and forms a covalent link right there. And some other secondary interactions with the enzyme that keeps this dead. The enzyme can't act on the D-ALA glycopeptide to form the cell wall now. It's inhibited the transpeptidase. That's the basis of how all drugs work, by the way. They're inhibitors of some process that we don't want to go on in a pathological, a pathogen pathway in disease. But let's see, bacteria are smart though. They're not going to take this lying down, right? They're going to come up with a way around this. So if they're exposed to high amounts of penicillin, they'll actually overexpress a certain gene called penicillinase, which is a drug-resistant enzyme that actually opens up the lactam of the drug and keeps inactive here. Once the lactam's opened up, this drug is inactive now, okay? And the bacterial transpeptidase, the enzyme needed to make the cell wall, is then free to form more cell wall. So synthetic chemists, medicinal chemists have to come up with new approaches to inhibiting bacteria. These things can mutate and overexpress penicillinase. All bacteria don't all overexpress penicillinase, but they all have different mechanisms for drug resistance. So there's a lot of different antibiotics that have been developed. These are the 5 main classes. The beta-lactams, the transpeptidase inhibitors, here they are. Here's the indications for what they're used for. Here's the potency, the MIC value, micrograms per milliliter MIC there. Yeah, and all of these are still used in the clinic for different applications. You've probably taken some of those. Protein synthesis inhibitors is a different pathway in bacteria. Bacteria have specific enzymes for them that are different than higher animals. So these are toxic to the bacteria, not to us. Chloramphenicol, tetracycline. So treat different types of bacterial infections. Streptomycin, erythromycin are RNA ribosome inhibitors. That's an independent pathway, independent of the cell wall and the protein synthesis, actually. Binds directly to the ribosome. It's part of the protein synthesis, if you know about translation in that. And then vancomycin and these are the last resort bacterial inhibitors. So if someone has resistant strains of bacteria like MRSA or other life-threatening infections that show up oftentimes in hospitals, unfortunately, they'll use vancomycin as a last resort, last line use, yeah. Completely different mechanism. It binds directly to the D-ALA unit in the forming cell wall. So it doesn't inhibit the transpeptidase. It actually binds non-covalently and keeps the cell wall from being formed with a different mechanism. Anyway, I like to show you enough of that, how that relates. These derivatives relate to a lot of things drug-wise, not just what we've talked about briefly, but here's Procaine, which is a analog of Novocaine. And where do you take that? Yeah, in the dentist chair. Numb up your gums before he starts drilling on you, right? So these are local anesthetic reagents that can kill pain, but they don't kill pain indefinitely, right? These are short acting. Well, they'll last for a couple hours. Your jaw will be numb for a while. But why does the numbness go away? Well, they're esters. So these esters are hydrolyzed over time, right? So that's the mechanism of it being uh, mitigated there, and the effect goes away. These are all based on cocaine, which is a diester found in nature from the coca plant, and this is how they were originally designed and thought about. The ester in the aromatic group approximates the position in cocaine, and then the tertiary amine here. And so these bind to the pain receptor in similar ways to cocaine. Cocaine's a non-selective dopamine reuptake inhibitor, and we'll get into neurotransmitters later when we talk about amines. But you can kind of see here, there are other generations of painkillers based on the same series here. These are amides, and these are longer acting ones. So the dentist or the physician in the clinic or whatever will prescribe a longer acting one if an operation will take longer, or if it's a short thing, just to fill a carry or whatever, use lidocaine or procaine. There's a lot of other variations here. These are 100 years old. These have been known for a long time. Right after the structure of cocaine was determined, synthetic chemists started designing other molecules that had similar activity. Hundreds of these type of materials have been tested. There's only a few that are available in the clinic, but they all relate to these carboxylic acid derivatives. Very good. I think that's it there. But let's do a little exam review here. Let's look at the sample test I think I've got on here. Where is it? There it is. We'll click through this here and we'll do a little mock quiz or test here in a second, see what we need to do there. And maybe I'll keep it big like this. Let me just keep it like that and I'll kind of scroll through it. I think it shows up a little bigger that way, doesn't it? It looks okay up on the screen, yeah. And it focuses okay. But maybe each time I scroll it, will it take a while to refocus? Is it refocused okay? Okay, yeah, you can see that. And also, you know, this is posted on Learning Suite too. Work enough of the problems in the chapters and review up to this point before you look through the sample test or those worksheet problems. Those are some harder problems, right? So make sure you go through these carefully before you start looking at the sample test. So there can be some nomenclature questions, of course, some structural questions, alpha, beta, unsaturation here. That's referring to the position next to the carbonyl. Number 3 here. Which aldehyde cannot form an enamine with a secondary amine? Remember, you need an enamine to form a secondary amine. Can all ketones and aldehydes do that? Remember, esters and other derivatives don't do enamines and amines, just aldehydes and ketones. But what do you need here? You need to have at least one alpha proton to be able to take off. And that's this one here. Benzaldehyde cannot form an enamine. There's no second proton to take off that alpha position. Acid-base chemistry, yeah, we had some of that on the quiz there. Sodium borohydride reducing an aldehyde or a ketone. This is a ketone. And we've got regular hydrogen sodium borohydride. So that's what adds here at this position. Then we quench with D2O. What's D2O? That's deuterated water, heavy water. And if we put in pure D2O, where's that deuterium going to end up? Well, yeah, it's going to end up on the oxygen because that's where the O minus is. Right here, we have a regular hydrogen, right? So deuterium allows us to track mechanistically what's the electrophile, what's the nucleophile, whatever. We could have deuterated forms of sodium borohydride or deuterated LAH, okay? And that would change the mechanism on some problems as well. Bond length, structure things, due to resonance, that's shorter, yeah. Naming again here. PCC, that's not DCC now. We're doing the oxidation there. Remember, it stops at the aldehyde. Grignard reagents with formaldehyde will give primary alcohols. Yeah, remember the different functionalized carbonyls. Formaldehyde, an aldehyde, and a ketone. Okay. Grignards also react with esters and acid chlorides. They add twice, right? Grignards are very versatile that way. Here we're hydrolyzing an acetal. This is an acetal. There's two ethers on this carbon right here. That's a methylene carbon. So if we hydrolyze that, treat that with water and strong acid, that becomes the carbonyl. And that's what? That's formaldehyde right there. Two hydrogens, go through the mechanism, protonate, transfer water on there, and eventually you get to formaldehyde. And what? These two on the side become dialcohol right there. So it's 2 and 4 is the answer for that one. Which intermediate? Conversion of nitriles to carboxylic acid. Oh, we just went through this. You can see all these intermediates, B, C, and D there. Why is A not an intermediate? Well, this has a hydrogen there. No, we're not reducing things, okay? So we always have a tetrahedral intermediate. We never transfer a hydride there. Okay, so we can ask you little mechanistic questions on multiple choice there. Highest reactivity for hydrate formation. Aldehydes are certainly faster than ketones. And yeah, if you have electron withdrawing groups close to the carbonyl, like 2 fluorides, that'll make water adding faster here, okay? And it'll have the highest percentage at equilibrium. I don't know if this one will form the hydrate completely and be stable enough for isolation. Probably not. If you try to isolate that one, it'll probably reverse right back off. Light harvesting, rhodopsin. Oh, so here's an application one. And this is covered in your book, and I mentioned it in class. So you need to know the connection between opsin, the protein, and retinal, the aldehyde, is an imine. Okay, iminium, yeah, it's protonated. Yeah, if there's enough acid around, it'll be an iminium, or it's certainly got a carbon-nitrogen double bond. So that's your imine. It's not an ester, an enamine, or an amide. The amine coming off the opsin protein is primary. Okay, so it's going to form an imine. Then we got micelles. That's the soap action, cleaning action, the macromolecular structures, non-covalently assembling based on the hydrophobic effect. Grease and dirt go into the interior and become solubilized into the polar carboxylate exterior there. So yeah, there's a couple spots we can ask you about applications. There's pimelic acid. We were just talking about adipic acid with nylon, right? Slowest rate with water. Well, there's a hierarchy of functional groups there, derivatives. Which one is the most stable? Yep, the amide. Okay, this would be the fastest. Tert-butyl, that's a hindered ester. That'd be next in slowness after the amide, and then isopropyl. Both of these would be slow, isopropyl and tert-butyl. Conversion of an ester to aldehyde, yep, Dieball. Interconversion of carboxylic acids typically involve what intermediate? Tetrahedral. Okay, no, not acylium ions. That's an alternative mechanism. Not acetals. There we're talking about alcohols with aldehydes and ketones. Certainly not radicals. What else have we got here? Oh, chapter 19 here, carboxylic acid, benzoic acids. If you have donors on here, these methoxys are strong resonance donors. That will push electron density into the ring. They're what? Orthopara directors, right? That will actually destabilize the conjugate base from this because that's anionic, right? Take that proton. Everything about how strong an acid is comes down to how stable the conjugate base is, right? So this conjugate base here is destabilized by 2 extra donors here. But if you have a withdrawing group on here, this nitro, that will help to stabilize this anion charge. So I think this is the strongest one. Weakest to strongest, yes, so 3 there you see is the strongest. Weakest is this one, yeah, and then you can figure those 2 out, I think. Thick starting material for formation of soap. Yeah, we just went through soap. Here's the acyl triglyceride, right? And this would have a stearate, long chain, 18 carbons there, including the carbonyl and the glycerate. Not this. This is a carbonate group. Carbonates are well known. Here the esters flipped around. Okay, here we need the carbonyl group out here next to the fatty acid, not toward the glycerol. That's incorrect. And then we have a polyamide here, triamide. That's not it either. Okay, This is the adipose tissue, acyl triglyceride, needed to make soap, either from plant oil or from animal lard. Let's see the write-on ones, and again, we can modify these to make them multiple choice now. And this is just, what conditions give what product. So Grignard addition there, LAH addition. Here we have our secondary amine with an aldehyde. So yeah, enamine there. Here we have an amide formation of the acid chloride. Here we have hydrolysis, so heat and acid. So that's showing acid with water. So it'll form the carboxylic acid. Thionyl chloride forms the acid chloride. And then ethanol forms the ester. Yep. So yeah, multiple step. And we could build those up. The synthesis problems, we can have multiple step there. Here's the cuprate doing the conjugate addition. Remember, you protonate the enolate there in the workup step. Per acid, oh, that's a 351 reaction, right? I think that's chapter 9 from 351. That forms what? MCPBA or any per acid with an alkene forms, right, an epoxide. Then you have the epoxide here. Then the Grignard adds on the less hindered spot, which would be out here. That pushes the alcohol over to that spot, the tertiary spot. And yeah, how do we get this 4-carbon unit here? Well, 1 carbon was already there on the epoxide. We added N-propyl. We added this 3-carbon. That's a very common mistake for beginning students, to lose track of the carbons, especially with epoxides. So this one's tricky, this problem here. We'll work through that, and there's similar ones, chapter problems. And then supply a reagent for a given transformation. So we want to make the ethyl imine, so we need the primary amine here. Here we want to make a ketone. So how do we do that? Well, if we make it from the alcohol, do an oxidation the last step, yeah. And so this would be isopropyl adding to that aldehyde. And this should have an alcohol, and then we do the oxidation, okay? So we know how to make ketones from a number of different ways now. Let's see, how about this one? Hydroxy carboxylic acid. So we got to add a carbon, the carboxylic acid, and an alcohol here. Well, if we remember this reaction, what's that one called? Right, the cyanohydrin reaction. Sodium cyanide and acid. Cyanide will add, and we'll get the cyanoalcohol. Then we hydrolyze the cyanide, okay? Leave the alcohol alone, okay? Yeah, you'd think, well, we could form the carbocation, do an elimination. Yeah, you can do that if you heat this up, actually do that, but if you carefully hydrolyze the cyanide, you can leave this alcohol alone. That one's a little tricky too, I think. Then you got your old friend here, the triphenyl phosphorane ylide. That's the Wittig reaction. Don't say Wittig. It's Wittig. And when that adds to an aldehyde or a ketone, yeah, we get the alkene product. Okay. This one's a few steps. Let's see. Just take benzene and form this N-N dimethyl benzamide. That's how you'd name that, right? So we need to put a carbon on there. So we start out by doing Friedel-Crafts methylation. Then we do the oxidation with chromic acid. That forms benzoic acid. Remember that cleavage reaction. That's from the previous section. That's chapter 18, I think. And then here's the reaction now, thionyl chloride to the benzoyl chloride, and then the dimethylamine, yep, forms the amide from the acid chloride, okay? That one's a little bit trickier. Here we have a complicated one, I think. Where do we get this isopropyl group from? How can we add here? And then what do we need to add here? Well, we need to add a couple things. Let's see. We need to do a cuprate addition here, and then we get a ketone here. Then we need to add, let's see, we need to add an ethyl. Uh-oh, here's a typo. I just flunked my own test. This should be ethyl magnesium bromide, because we need to add this 2-carbon unit to this ketone right here. You see that? Okay, yeah, I am fallible. I do make mistakes too. Not many, but I make some. Okay, yeah, that should be ethyl magnesium bromide. All right, MCPBA, and then opening up that epoxide right there. Yeah, those are the trickier ones with the Grignards, I think. Practice those epoxide ones. Then we got a multi-step one here. You're told to make this starting with any alcohol. So here's a complex amine, right? And what you see here is you got an isopropylamine part here, and you know how to make different amine groups here. So if we have a double bond on either side, there are different ways to approach this molecule. the easiest one, and the one that I saw in the literature years ago anyway, came from this imine here and then hydrogenating it with palladium, reducing that double bond. Remember we talked about reductions of imines and enamines and ketones and aldehydes, whatever. You can do that with palladium and hydrogen. And if you do that reduction, then you can come to this. And so if you have this intermediate, look, you can make that from what? A primary amine, this isopropylamine, and this ketone. So that's why I started thinking about isopropylamine up here, and you can see how to make that, right? And then you got to make this ketone. That's the key thing. Well, we can make from an alcohol, and that allows us to do a Grignard addition, right, to this aldehyde. Oh, and look, I flunked right here too. I needed to show what a reagent right here. PCC or chromic acid, yeah. Yeah, why I'm flunking my own tests today. I don't know. I've missed 2 so far. Ruben's not happy out there. I don't know. No, yeah. Well, yeah, so not many points. Well, 6 points. There's a lot of steps in this reaction. So making the Grignard, you got to make that from a bromide. You make the bromide from an alcohol. PBr3, remember we said that's the best way to take an alcohol and convert it to the bromide without any shifts. So you see here, there's branching next door. If you just use HBr here, you get tert-butyl bromide, not this isobutyl bromide. So yeah, you need PBr3 here. And then the Grignard reagent, and then this aldehyde you can get from that alcohol, and then yeah, and then you're off to the races. I think you can see how that goes together. Work backwards on those synthesis problems. Oftentimes you see the key steps from the back, and then see if it maps on to a reaction that you know how to do. That's another key way to approach those problems. This one's just a mechanism one that takes forever, I think. This is ammonia, which is going to form an iminium ion, and then there's cyanide nucleophile in there to form this cyanoamine, and then it's just hydrolyzing the nitrile, and we just went through that mechanism. And eventually that gets to this, an amino acid. This is phenylglycine, an amino acid. And you're doing it from the aldehyde here, adding to form the imine first, and then cyanide. Hydrogen cyanide, that's a dangerous reaction. Not allowed to do that on large scale. It's a very toxic material. There's other ways to do that. You can have the sodium cyanide and HCl in there, would also allow this reaction to go. But yeah, mechanistically, that's all your, and this is a reaction we didn't cover actually, but we've covered all these reagents and you're given the product. So here you have to come up with a mechanism. So this is a tougher problem, but on these ones where it's not a reaction we're familiar with, we'll show you the product, okay? But you ought to be able to come up with a logical mechanism. This is a tricky one too, this pyrazine, this aromatic dinitrogen thing here comes from the alpha chloro, acetophenone and ammonia, then heating it up with oxygen. And you're told here your byproduct's peroxide. So something had to get oxidized for the oxygen to get reduced to peroxide. And so it starts out with iminium ion formation, iminium ion, and then here's where it dimerizes. You've got to put 2 molecules together. What type of reaction is that? Right there. So this nitrogen lone pair attacking a primary chlorine. Yeah, it's an SN2 reaction. Okay. So another SN2 right there to put the ring together. And then you got to take off some protons here to get to the dihydro intermediate. And then, yeah, the tricky part here, and when we did give this problem a couple years ago, we let you off the hook on this last step here. Didn't expect you to know how to do this. Some people nailed it though. If you take off a proton, flow the electrons around, you get to the aromatic thing here. But then you got to flow hydride out and reduce oxygen, and then protonate the anion there to get the peroxide. So we actually gave you enough information to figure this out, but this last step we thought was too tricky. If you got the rest of the stuff, the imine and the SN2, you got full credit there. All right, these worksheets, we've got a couple minutes here. We're almost done. Oh, okay, we're probably a little over already. Worksheets here, work through them. These are harder problems. pKa stuff, which base can deprotonate which acid. You're comparing pKa's, right? and I think you're comfortable with that now. Ascorbic acid, the resonance stabilization, I think answers that. Here's some synthesis problems, mechanism problems, stuff that's a little bit different. This one's quite a bit different. A very bulky ketone and an isopropyl grignard actually does a reduction, can transfer hydride here, which is kind of unusual. It gives an equivalent of propene, which is kind of cool. But yeah, that's not a reaction we covered, so don't be too confused about this. There's a propene byproduct here with this hydride coming out. And then we got some synthesis ones. We've been talking about epoxides. I think those are okay. Chapter 21, ketones, aldehydes. This is just a diimine thing to form this cyclic dicarbonyl compound going to the pyrrole. Another epoxide here with a Grignard reagent, or a Wittig reagent, sorry. And then you deprotonate and form a different ylide here from the epoxide, which is kind of neat. But there we give you the product. So that's definitely a harder problem. This one relates to sugar chemistry. We'll see a lot of this later on in the sugar chapter. These are acetals from the cyclic hemiacetal. And then the mechanism here, adding methanol top or bottom to give that product. And the last one, a couple things on acyl transfer, cyanide chemistry. Yeah, this one here is just some variations, I think, of putting together with an acid chloride how to make those pieces. Yeah, you need some SN2 some 351 chemistry. Well, Friedel-Crafts allylation right there. Hydroboration, yes, 351. Carbonate chemistry here. We're giving you some carbonate and urea products here from this guy. Okay, phosgene it's called. But you can follow that. It's just kind of a double acyl transfer, really. This kind of relates to Gorilla Glue. You've probably heard about that stuff. That forms a polycarbonate once it cures. That eliminates water. Very strong material, carbonate. A couple different precursors to that in Gorilla Glue. But it follows all the mechanisms we've been looking at, tetrahedral intermediates, whatever. So yeah, sorry we didn't have time to go through too many of those on the worksheet, but I think you practice those and work on those, you'll be okay seeing the test and the material. Yeah, our test will be representative of this difficulty, but it'll be 40 multiple choice questions, right? So it's a little bit different that way. They're worth 2.5 each. Most of them are single concept questions. Some combine multiple concepts, and we can reformat some of these trickier problems for multiple choice also, but it won't be all a bunch of tricky problems. Don't worry about that. Most are single concepts. So very good. Happy studying, and we'll see you next time. Very good.